Let me introduce Ilya Baldin from the University of North Carolina, who is a leader of a very interesting project. Basically, in my own words, I would put that as a next generation cloud for research, probably. So it offers some very interesting features for researchers all around the world. So Ilya, please tell us more.
Thank you for giving me the opportunity to give this talk here. Yeah, so let me start sharing my screen. Without further ado, I'll present. Okay, you can actually see it. Excellent. Full screen. Hopefully this will go full screen. So yeah, I'm here to talk about Fabric. It is a project funded by the National Science Foundation in the United States a year ago. We are 1 year into a 4-year construction project. In this talk, I'll kind of introduce briefly the various aspects of what we're doing, and then in the follow-on session, those of you who are interested, please join and we can have a discussion about this. So just first, really quickly, the participating institutions. There's a core team of University of North Carolina, Chapel Hill, University of Illinois, Urbana-Champaign, Department of Energy's ESNet, University of Kentucky, Clemson. These are the core institutions participating, and then there's a number of supporting projects or supporting team members in the project that hail from a dozen other institutions that I just don't have time to go over today. So let me just get straight to the motivation. Why are we building Fabric? The short story is that basically, if we were building a router today with the economics of compute and storage that are available to us today, it is very likely that the router we would build wouldn't look like the ones that we have today. There's a strong argument that the architecture of routers essentially follows some legacy assumptions that are no longer true, specifically when it comes to the cost of compute, storage, memory, etc. So what that really lets us do then is start thinking about, what if the internet were a more stateful architecture, had a more stateful architecture? And I take the definition of the word state very broadly. It could be control plane state, it could be data plane state, it could be actually hosting applications within the network. In fact, sort of as builders of Fabric, we try very hard not to bias our thinking with any one of those directions. What we're trying to do is build a facility in which experimentation with these different aspects of architectures and distributed applications can take place at a large scale. So, there are other kind of breakthroughs, recent breakthroughs that are kind of feeding into this. And, few to note are, of course, machine learning and AI revolution, right? Now you can now start thinking of a network, not just something that transports big data, but generates big data and acts on that big data. And that could be related to the control, but also, again, to the applications hosted within the network, thus creating more of a continuum of computation capabilities. We don't just design applications for specific architectural inflection points like, oh, we're going to put this at the edge, or we're going to put it in the cloud. With Fabric, you can put it everywhere. Of course, network vendors are looking at the ability to autonomously drive networks using a concept of like a self-driving network. And of course, there's IoT, 5G, and closer to us academics, there's science applications. Today's science strongly depends on the ability to acquire, store, process data. And if a network becomes part of this continuum where data can be processed, there's a potential there to improve the productivity of science. Going on to the next slide. So what is Fabric? Fabric is a nationwide programmable network with compute storage capabilities built into each node. So where you have routers. In Fabric, you have these nodes that have combined computational storage and compute, and as well as networking capabilities. We provide GPUs, FPGAs, network processors. It is a sliceable environment that experimenters can essentially create their own topology in with the desired properties, launch their experiment, collect the data, and become famous. Fabric also interconnects national facilities because in the United States there is a rich environment in which scientists operate today. There is HPC centers, there's open science grid, there's public clouds, there's institutional clouds, there's various test beds. So Fabric, by design, interconnects many of those together, thus creating kind of this environment in which experimenters can pick and choose more production-oriented, more experimental-oriented facilities to stitch together their experiment and run at a reasonable scale. This is a picture of the envisioned topology. I won't spend too much time on it. It's just to point out that this is a 100 gigabit network with the blue links shown here. And then the yellow is what we call a terabit supercore with 1 to 1.2 terabit per second anticipated capacity. And importantly, this is dedicated to experimentation, right? This is not a production facility. This is not something that you just daily, use to watch YouTube or a Red Hat conference. No, this is specifically dedicated to experimentation. What does an individual node look like? Well, conceptually, it looks sort of like this. There's a bunch of worker nodes. There's a head node. They're equipped with different types of resources, typically PCI devices, network cards, GPUs, FPGAs. And the idea is that the experimenters can essentially get virtual machines or containers directly attached to those devices so they can full control of those devices. And they stitch them into, or the Fabric software helps stitch these together into large slices or topologies across the country. Where, again, experimenters can collect the data, run their application, test their ideas, and come to important conclusions about what the future internet might look like. This is just a little bit about the hardware details of what these look like. Not terribly important probably for this talk, just some, name dropping, GPUs, FPGAs, Xilinx FPGAs. For those of you who are familiar with networking and the P4 protocol, there's we're working on supporting that through FPGAs. There's also kind of hardware offload through ConnectX 5, ConnectX 6 cards, multiple interface speeds, etc., etc. And then storage at every node, anything from memory to basically a hierarchy of storage, anything from memory to NVMe drives to rotating storage at each site, so you can again allocate that and attach it to your experiment. The important portion of kind of our thinking about Fabric is the measurements. It's a scientific instrument, and therefore we have to figure out how to get data off of it. How to measure important things, how to get that data out. So one of the bigger questions is time synchronization. In today's internet, of course, routers typically aren't synchronized, or they don't take advantage of that information. However, in Fabric, each site is going to have its own GPS disciplined clock with PTP available to experimenters. So in principle, you can take a snapshot of packets going across the network with fairly accurate sort of millisecond accuracy timestamps all across the network. And of course, measuring more traditional things like CPU, memory, disk utilization, we're going to have some level of optical layer measurements, even though Fabric itself isn't intended to have an agile optical layer that you can switch or the experimenters can affect. Nonetheless, measuring that could be useful to some types of experiments that look at cross-layer operations within the networks. So, if I were to just sort of abstractly try to explain what an experiment on Fabric might look like, it would look like something like this. It's deliberately superimposed on top of the map of the United States just to show that this is done at large scale. This is not in the lab. This is done across the entire country. You can have an external resource, a supercomputing center, your local cloud, your public cloud attached, and maybe sending traffic to a node here, maybe in the center, but maybe you want to do some measurements, kind of bump and wire type measurements. And this is where you would use, again, a virtual machine or container that's attached to a PCI card, a 100 gig card, it's passing all your traffic through. Maybe you're sampling it. Maybe you are doing some inference on it. Maybe you're doing some accelerated processing using FPGA. This here might act more like a kind of hard-soft combination switch with a lot of hardware acceleration in the cards, but some software in between. You might be, you might have pieces of a distributed application that requires super fast cache within the network, and it relies on NVMe drives and some GPU processing perhaps to fulfill its function, and so on and so forth. The possibilities are almost endless. This is just kind of to show very, very, very briefly the flavor of things that are possible. Of course, what makes it all work is software. We're building a software stack, which sounds scarier than it actually is. We're using a large amount of off-the-shelf software in order to make our job easier and only kind of adding value where we have to. But there are really kind of several major components. There's what we call a control framework that does the provisioning of the resources. There's a measurement framework that helps experimenters collect measurements. We have an information model that helps describe resources for provisioning purposes. And all of this is linked through a message bus. There's an authentication system, user interface tools. And because all of this is based on services, as an experimenter, it doesn't matter too much how you decide to interact with the system. You could do it through a graphical portal, which we're building, or you can do it through a Jupyter notebook with libraries that we're building that will interface with the various APIs and the control and measurement framework, so you can build your experiment and measure data. There's a common authentication system, common authorization plane to all of this, so it doesn't really matter how exactly you choose to interact with the system. I think I'm going to skip this slide just because of time constraints. So the slide, you can see the detail of what the user tools might look like. You can see that there's basically 3 different ways that you can do it. You can just do it from your laptop. You pip install the tools and you interact with the system. There's a hosted set of tools via Jupyter Hub. You get you log in using your federated credentials. You get a notebook which has all the tools installed for our test bed, for other test beds, and you can build your experiments there. Or you can do it through a portal, which is more suitable perhaps for education, for kind of hello world type stuff, where you're just learning the ropes, as it were. Let me skip the authentication system and services. I'll talk a little bit about it down the line. So the control framework basically is built on a number of existing components. It's important to note that the control framework is seen as an overlay on top of existing IaaS systems. So for instance, each individual site is run by an instance of OpenStack, excuse me. And we also have other systems that we're interfacing with, like Cisco and SO, and then there's other network control plane options there. Of course, user tools are done via Jupyter Hub. Message bus is Kafka. Authorization service is done through something called AuthZForce CE, community edition out of a project from EU called Firewire. Information model is based on property graphs stored in Neo4j. So while we are adding some code, we're also using a lot of off-the-shelf systems. And basically, the control framework consists of 3 types of actors: an aggregate manager that sits on top of each site and also sits on anything controllable. Basically, any controllable resource has its own aggregate manager. And there are plugins that help the system kind of be customized to the specific resources it's controlling. There's a broker, one broker that collects information from multiple aggregate managers together and then presents it to the orchestrator, which helps users build their topologies. The users interact, as you can see, with the orchestrator using a user-facing API. They express their requests using the fabric information model. Orchestrator kind of finds out what resources are available from the broker, uses embedding algorithms to essentially instantiate the desired topology, and then all of the communication happens over message bus. And then there's a common authorization service that makes sure that the users don't exceed their permissions. It's very important that this authorization service is distributed, because we in Fabric deal with sometimes contributed resources. So somebody comes to us and says, well, I have this resource, I'd like for you to be able to control it. So we can't just say, oh, well, here's a big centralized permissions management system that we're going to set it up. We're going to set the permissions for you, but you really won't have any control over it. No, the idea here is that the owner of the resource actually has significant control over how their resources are managed, because they have their own policy enforcement point sitting that they control and configure, thus allowing certain types of users or disallowing certain types of users or certain types of experiments to proceed on their resource. So I think I've mostly talked through all of this already, so I'll skip. The measurement framework is responsible for managing the measurements. It's counterpart to the control framework, and they kind of intended to work together in concert. For instance, the control framework may provision additional resources for measurement framework based on the request from the user as to what needs to be measured. It may provision, capacity to actually move measurements, for instance, around, which could be significant if you're dealing with a network with 100 gigabits per second. Some experiments here shown. Again, you could do sort of, if this is a Fabric node, maybe you're just ingressing and egressing through the switch and you're not actually dropping any traffic locally on the node. Or maybe you're dropping it and using OVS offload to just kind of stay mostly in hardware. Or maybe you're hosting a whole application that uses some of the built-in capabilities I mentioned, GPUs and NVMe drive storage, to support the application needs. And of course, on top of that, there's GPS synchronized clocks available in each site, so you can take very precise measurements of what's going on and ship them off for analysis. This is a conceptual kind of drawing of what the measurement framework looks like. Also relies on a large number of existing open source projects like Elasticsearch, like Ilk, and all of its components, Logstash, Kibana, etc. We've also not shown here have already finished deploying Prometheus for collecting metrics out of our infrastructure as well as out of the experiments. Actually, it's Prometheus with Thanos. And Kafka, again, serves as a message bus. For authentication and authorization, federated identity is very important. We're dealing with academic researchers, come from multiple institutions. A lot of them have what's called in common. Today, it's run by Internet 2, so that means that we can get their identity attributes released to our portal through a project called CI Logon, run out of NCSA, out of University of Urbana-Champaign. And all of this essentially is linked to this. So CI Logon, as those of you who are familiar with Auth0, is a very similar thing. An important design decision for us is decoupling authorization from the rest of the system. So we went with attribute-based access control, which means we can have multiple sources of attributes on the identity instead of a single monolithic place where essentially a role gets assigned. And this allows us to support resource provider independence. As I mentioned, policy enforcement points use different policies under the control of the owners of the aggregate rather than a single centralized policy. And also, in the world of these test beds, there are a number of test beds that have preceded Fabric. It's typical to rely on client SSL certificates to authenticate users, but that has created some problems with essentially building chains of tools where one tool invokes another, and then finally invokes the control framework, for instance. You really can't do that with certificates unless you start issuing, speaks for credentials, which are, tricky to manage. So instead we went with a token-based system, but not a capability-based, but again, an attribute-based system where tokens carry attributes of an identity signed by an authority, and then individual PEPs, policy enforcement points, make decisions about permissions for that identity based on the attributes contained in the token. And that's it. Please visit whatisfabric.net for more information. There's a button there called Get Involved if you want to sign up for a monthly mailer to learn more about what we're doing. All our software is open under MIT license. We're furiously developing it right now. It's under this GitHub URL. And I look forward to your questions.
Yeah, let me start with the question. So you said this is you talk a lot about authorization and permissions and so on. So who will have access to this to Fabric?
Right. So right now we're building the mechanisms to implement the policies that will be put in place. The project is still in the construction phase. There's nothing for anybody to use yet. So we're trying to retain as much flexibility going forward as to kind of what policies we might put in place. But if I were to kind of look into the future, I think the policies might look like something like this. If you are a student at a U.S. institution, you can basically using your institutional identity log in. You can join one of the existing projects. You have to request that. So, maybe there is a faculty member from your institution that already has a project within Fabric. And then you can start creating slices on Fabric topologies for your experiments using that. We are discussing kind of interactions with the industry, for instance, and this is kind of, there are multiple, answers within answers, I suppose is the best way I can put it. If it's a open research kind of a topic, and essentially it's industry partners and academic partners working together, I think that's a very easy, positive, affirmative answer. Sure, come and use it. If it's a question of, can we do proprietary research on Fabric that, my competitors won't find out? We are considering it. We have not made any decisions. Let me put it this way: we're actually looking for feedback from our industry partners as to what they want to do, because we can put a lot of effort into making it possible to do kind of private research, well protected research on this. But the question is, is it actually going to be? Is it a matter of curiosity, or is it really something that they want?
Yeah, I think for Red Hat, with our connections and cooperation in universities and researching not just in the US but all around the world.
And federated identity in common covers not just the US, right? In the European Union, there's a lot of institutions that have in common already. So it's in South America, we know. We anticipate that this will be relatively easy to federate or use federated identity from a lot of places around the world.
Do you have plans to add actual nodes and clusters from other parts of the world?
Yes, that's actually an excellent question. So yes, so far everything I've shown you has been very US centric. However, we just actually got word about a project that we call FAB, Fabric Beyond Across Borders, FAB. And that project will pay for additional sites in Japan, in the United Kingdom, at the University of Bristol, at the University of Amsterdam, and at CERN. And as I mentioned, part of our model does include contributions of hardware. In other words, you can find a bill of materials from us and buy your own node and talk to us about how to connect it to the rest of Fabric. And oh, by the way, you get a lot of flexibility with respect to the policies of who gets to use it.
Okay, so we have a few questions in the chat. So Hugh is asking, or maybe rather adding a comment, that there seem to be some interesting applications for multi-cluster work.
That is a very, very loaded question. So, I think, let me try to interpret this question in my favor. And I think maybe the question here is, have you guys read of all the multi-cluster work in Kubernetes and OpenStack, etc.? Yes, we have. Part of the reason why we're rolling a little bit of our own here is because we need to be able to offer very, very different multiple network services. And we also need to be able to control non-OpenStack, non-Kubernetes, whatever else clusters. So if I know I was flashing slides very quickly, but the idea behind our aggregate manager is that it's very pluggable. That you can, as long as something underneath it has an API, it could be Proxmox, it could be something else, right? We can write an adapter to it. So if you have a resource that's controllable through API, there's a good chance we can put an aggregate manager on top of it. So we don't want to be we want to take advantage of a lot of this development that's done in these projects, OpenStack, Kubernetes, etc. But we at the same time don't want to be locked into their roadmaps, because we time and time again we keep finding out that the requirements we have in these systems, while looking similar at 50,000 foot level, start diverging with what a lot of times the community is building. One good example is we want the ability to provision things, virtual machines. Sure, that's why we're using OpenStack. But a lot of the schedulers in Kubernetes and OpenStack, they are geared towards utility, highest utility, packing the densest kind of possible combination of compute instances. That's not what we want. We want reproducible experimentation, which means we want isolation. So utilization to us is not a very high value metric. We'd rather that the experimenters can come in one day, do an experiment, come back the other, and have very similar results, regardless of who else is on the testbed.
Yeah. I think we have time for one more question in stage. Barbara is asking that you were talking about putting more state into the network, but IETF is taking that actually out with segment routing. So she's asking whether this is more applicable to the network edge for various applications.
Can you repeat the question? Sorry.
So she's. You can read. My understanding of the question, and Barbara, please correct me if I'm wrong. My understanding of the question is whether this research is applicable to.
I saw the question. Sorry, I just read it. It's probably best taken off into the session. I'm not sure I'll be able to provide a very quick answer to this, but this tension between adding and removing state has persisted for a long time. And our goal is to enable the experimental community, the scientists, to experiment with it and render a judgment whether this was a good idea or not. This is not a production facility. This is a way to explore the state. The way that IETF is going about it, there's vendors involved and they have their own agendas. They have their own preferences of how they want to do things. That's not how sort of architectural research works from my perspective. What we want to provide is the ability to experiment. At the end, it is entirely possible that the community will come back and say, you know what? IETF was right. We shouldn't really put state in the network. It's a bad idea. I actually am betting that that's not going to be the answer. We are very deliberately, like I said, trying not to bias our design by any specific view of what the state in the network might look like. As I said, it could be control plane state, could be data plane state, could be just application state. Caching in the network exists for a reason, right? There's a reason there are companies out there that cache data for videos and web pages, etc. Except they can't really do it in the network, right? They have to do it at the edge. So why can't we have a network where you can do it in the core? So there are definitely use cases for state in the network.
It was interesting point about the edge computing and stateless networks and all of that. So I don't think that in practice what we're seeing is moving of the logic to edges, like not all of that. But yeah, hard to predict what will be the trend in the future.
Well, I mean, you can see some of this happening, right? So AWS now has what they call Spectrum service, right, which is kind of closer to the edge, smaller data center. There are a couple of kind of dedicated companies that are doing this. The name escapes me right now. There's of course Akamai, right? Existed forever now, and they do all the caching, right? It's a perfect example of why we need state in the network. Security applications, a number of others.
That's for content, though. That's not for like routing logic and all of that.
So as I said, I'm not trying to. We're trying not to bias our thinking, whether it's going to be data plane state or control plane state or a combination. Right? I mean, it's there is a large project, a community at this point out there supporting this idea of something called named data networking, NDN. Right? That is they've developed a suite of protocols and applications that runs at this point that are completely non-IP, where you reference not endpoints of the network, but you reference data objects, right? So you kind of it's a merge between I'm doing them a great disservice by speaking about their design, but it's a merging of data storage and data transport in one system. One way to think about it, right? The network intelligently automatically caches data objects and makes it efficient to distribute them. And as I said, this is this is not an overlay; it's a completely non-IP based suite of protocols.
So one interesting thing that that's been happening, and now I'm talking like from Linux point of view, like Linux kernel point of view. One of the interesting stuff that's been going on for past few years was focus on how to support hardware offloading, meaning offloading the logic from the CPU, from the software to like the NICs and other hardware. So to me, Fabric seems to be quite interesting project to experiment in this area.
We're definitely on the most, I would say, at least for the moment, we're mostly on the receiving end of developments in that area. In that, for us to make Fabric as multi-user as possible, we need those capabilities out of the hardware, right? Because the more we can offload the more our experimenters can offload to the individual peripheral devices, essentially, the more we can do with the testbed. I sometimes kind of half jokingly refer to, Fabric is more or less kind of it's a PCI real estate play. What we're doing is we're putting a bunch of servers together, making their PCI slots available to experimenters of the different things that sit in those PCI slots. And over time, you can change what sits in those PCI slots, right? If a new GPU comes in, we can swap them out, right? If a new NIC card comes in, we can take it out and put a new one in, and so on. And there's definitely, I've seen, a lot of development in that space where, a server becomes more of a shell for distributing to applications the hardware capabilities of different peripheral devices, right? So we're very much following that arena or in that space. To kind of follow up on that, the other interesting developments we're very interested in is the virtualizations of those devices. Right now, I very deliberately said, we are just giving out a device as a whole, because things like SRIOV and they're available, but not everywhere, and they don't always work as expected. But if they did, that would allow us to subdivide like a 4-port NIC into two 2-port NICs. Or particularly GPUs, right? GPUs are expensive. I know there are solutions out there, and then there's more actually coming online as we speak. So by the time we're done constructing Fabric, things might look quite different. But if we could take an expensive CPU and slice it 2, 3, 4 ways, that to us is a win, because so long as that slicing is done in a performance preserving kind of fashion. So in other words, the various slices don't affect each other too much. I'm going to use air quotes. Because nothing is perfect, right? Even within the server, right? You have NUMA affinities. You have, you need to consider how the bus is actually arranged before you make any judgments as to which part of one experiment is going to affect which part of another experiment. But abstracting just a little bit, we definitely are interested in advances in that space.
I had a question getting back to the topic that some of the earlier speakers.
Heidi, I'm sorry, Barbara was asking question in the chat.
Oh, I'm sorry. Go ahead.
Ilya, do you see the question, or should I read? I will read it out.
Yep. Yeah, she says her video keeps
So she said she thinks that framework is great to determine how well new protocols and processes will work. And she's asking what type of protocols are you thinking of?
So Barbara, please visit our website and click on Get Involved. I encourage you to do that. We will spam you, but just a little bit. You'll get a monthly mailer. We're nice. Don't worry. And you will definitely learn more about it. But to answer your question, one of the prime examples that is kind of the most developed within the community, and I'm talking about the research community here, is there's something called named data networking. I don't know if you're familiar with it. You can answer me through the chat if you're, if that's convenient, because I'm watching it. So you can look it up, NDN, or named data networking. As I was talking to Jiří earlier, that is a one prime example. Yes, it does sound like Lisp, but don't tell them that. Yeah, but it's actually a full suite of protocols. All joking aside, it's a large community, very well developed community. There's a NIST, National Institute of Science and Technology, actually has a group that works with that project and develops software with them. They have something called an NDN forwarder, which is essentially a router piece of software that they've demonstrated being able to push it. I think their latest, there's papers about it. Their latest was 6 gigabits per second on a 100 gig link using one thread. So they actually think with multi-threaded, they can fill in the pipe. And you have to keep in mind their processing of their packets is much more complex compared to IP, because they're dealing with data tags and data objects. So because each router essentially, if you think about Akamai on steroids, it's again a very, very simplistic way of talking about NDN. And if anybody from NDN project listening, forgive me, I am trivializing to a very high degree here. But the point being that there are examples out there, and there've been more examples in the academic community of these architectures, stateful architectures, or non-IP architectures. That tend to be the ones that are non-IP tended to have some state in them in different ways. So one of the things that we're trying to achieve with Fabric is kind of stimulate some more of that hands-on research rather than just writing academic papers or doing small-scale prototypes on Fabric, because our underlying kind of lingua franca, as it were, are essentially layer 2 connections. This is what you get on demand typically within Fabric. Then on top of that, you can build your own layer 3 or layer X, right? If you don't want to really think about it in terms of ISO model.
For people who are interested in interconnections, like off to Chameleon or off to other experimental networks, or perhaps even to commercial networks, are you doing that in some sort of a peering way, or are you doing that by calling those things resources in Fabric, or how do you plan to manage that sort of thing?
Yeah, so there is a design now that we've just actually completed. We're reviewing it to do exactly what you said, peering. I didn't go into it too much, but just because of the time constraints. But Fabric is going to actually, this has happened since it was not a major part of what we proposed, but as we started talking to the community, we realized that this was a big part that what they were asking, and that was essentially a persistent layer 3 service. So Fabric will have a persistent layer 3 service, experimental, it's intended for experimental uses, not for production, but it's going to be there. And so naturally this will be peering with production networks, right? So we have Internet 2 as part of our team. We're talking to multiple national or the regional networks in various regions of the country to make sure that that happens. In addition, there will be a capability to essentially start a layer 3 slice and then peer that with a production.
Mm-hmm.
And again, we have designs on the board. We're actually working with a peering test bed out of Colombia, Ethan Bassett. And that's part of kind of the capabilities we're envisioning to build up. It is interesting that Barbara Fox brought up MPLS segment routing, because actually our underlying technology within Fabric network substrate itself will be MPLS SR. But that's just to provision connections between the different ports in different locations, right? And we needed that. Testbeds are, as Heidi, as I'm sure you know, testbeds are funny animals because people think about them as experimental, but the underlying capabilities have to be production grade for people to experiment on. Otherwise, you get a lot of complaints saying, "Why doesn't it work? I tried to create a slice and it didn't work. You guys are terrible." So for that reason, we've actually chosen a pretty robust implementation. We're working with Cisco to make that happen. Make sure that we can create these different types of services.
That's very cool. So my other question was about what some of the previous speakers mentioned about people who are trying to do experimentation and therefore want as much reproducibility as possible and ways to record what happened in the work at the time they were experimenting. And I assume you're building some tools or something to help with that.
Yes. So that's the measurement framework portion.
That you very briefly mentioned, so we can dive into that.
I was trying to cover as many topics just to see where essentially the interest would lie. So yes, there's a measurement framework built on a lot of open source tools. So originally, I think we thought we would be doing actually more development, but we ended up looking at what open source community has to offer, and we decided we have nothing to offer other than just use it well in mostly intended ways. So we're going to be relying on ELK. That's part of it, particularly for things like log messages. Then Prometheus and Thanos for numeric metrics. Kafka as a messaging capability. Ceph as a backend storage for a lot of these, because we want everything, right? We want S3 capability, and we want scalability, and we want this and that, and we don't want to do it ourselves, right? So, one of the big problems with measurements is no matter how fast your network is, and ours is 100 gigabits, but it really almost doesn't matter. Once you start sampling a significant amount of traffic out of the network, then you need a significant amount of bandwidth, which is in some way proportional to the link speed that you're dealing with to actually get that data out. So it's almost like you need two networks. You need one for measurements and one for experiments, which of course we can't really do. So part of our solution is using local storage to the extent possible. So in other words, if you're sampling a significant fraction of a 100 gig link, your data better stay put on that node. We'll give you some fast NVMe drives, some rotating storage. You have GPU and FPGAs to help you sample, but there are some constraints there. And then you get that data out, right? For kind of low volume, low velocity data, you can use measurement bus, Kafka. We're currently running 2 Kafka instances already. One tuned for messaging, kind of reliable messaging for control framework, and then the other one specifically for data higher volume. And then I think the third option is provisioning additional capacity parallel to your slice within the available capacity to just get the measurement data out, which is what I mentioned. So that there's we anticipate an interface between control framework and measurement framework.
And you do have the advantage that you can store it locally and pull it out later more slowly, because you don't usually need the measurement.
And in fact, we just had a discussion about it, and Paul's going to be looking at how do we link. So many universities, at least in the U.S., and I'm just trying to be cognizant that we have an international audience here, but in the US, many universities have struck deals with the likes of Google and Microsoft to use their cloud storage, and frequently it's unlimited. You know, if you're a university student, you can get unlimited storage on one of those systems. So, you know, for us, you know, the problem of data storage is of course very acute. But part of the solution could be that we just, you know, make it possible for researchers in some relatively friction-free way to get the data out of our system and put it in one of these big cloud storages or on their campus, for that matter.
So in the Mass Open Cloud, we're trying to do the same thing of having the measurement data and the usage data available to be shared for experimenters. But, you know, keeping all that stuff around for years is not feasible. So
it's cost prohibitive. Yeah, so our design, University of Kentucky is responsible for designing measurement system. Jim Gerkuin, who I'm sure you remember. He's you know, he uses kind of this concept of a tap that you can open on demand, right? So we're not going to collect this data indefinitely and for no reason, right? You can tell us start collecting the data, and we will start, and that's a likely scenario, right? And we will, you know, we will keep it for a while. Unfortunately, it doesn't answer some of these questions. I think, Paul, you brought this up. You know, when COVID struck, right, it was very interesting. If you had data from before COVID and during COVID, you could compare behavior on the network in any other way. So that model doesn't work if you're only collecting on demand, because you know, your demand comes in when the event happens, not before. This is a hard problem.
Yeah, that's really interesting. We're starting to work with the University of Kentucky too at Mass Open Cloud and Red Hat. So we should definitely coordinate, because we could make tools actually work between two different environments that are collecting data in experiment.
I think that would be awesome. We are trying to do ourselves only the parts that we feel like we have a significant value add. And if we can partner, especially for, like I said, interoperability reasons, because of course Mass Open Cloud is on the list of facilities for us, because we're going to be at MGHPCC, right? We actually are discussing right now when the rack there, the fabric rack, is going to go in. So, you know, Massachusetts is very rich with these resources, and so we very much are interested in both connectivity as well as
so what happens when we try to take the 100 gigabit network and connect people like Jiří in Brno to it with, you know, some kind of an experimentation that means something and isn't just, hey, I can say hi to Brno. Like, what do you deal with, you know, latency and all of that stuff coming into the picture at that point?
So I guess I'm not.
So I'm sorry. In experimental networks that I worked on before, there was always a problem of the link that would get you from the US to anywhere else being a very long link compared to, you know, everything that was, and yet you have research partners who you really want to do interesting work with. Did you get some special high-speed links or something to deal with that, or is it the same usual problem?
Part of Fab, the project mentioned, the fabric across borders,
which
is actually relying on. I think you're probably most of the audience is not familiar, but Heidi, I think you are. Is IRNC links that NSF, National Science Foundation, pays for. And so they're going to, you know, there's indication they're going to make capacity available to us. Now, we can do nothing about latency.
Right, but capacity.
If we did, you know, there's a Nobel Prize in there somewhere.
Sorry.
Yuri's working on it.
And further, there's Fab. The whole point of it is that we're going to have fabric sites in Europe. So, like, your closest site will be, you know, in the same continent, you know, potentially.
Right, we're going to have like Bristol, University of Bristol, University of Amsterdam.
It's quite valuable to having actual latency for research, because there's only so much you can do with emulation, and latency is not going to go away. So having that and being able to run experiments over like real transatlantic link, that's Yeah, that's useful for something.
And not only a transatlantic link that you set up the path. So like if you come back in 6 months or a year and you want to do the same experiment, you can get that same path with probably has the same latency. Whereas if you're using the internet or something, right. If something changed, you might be going the other way around the world and the latency is totally different, right?
Yeah.
Yeah. So it's controlled. You can actually do an experiment on it. I'll add to you that going back to Heidi's original question, which was like, how are we going to do repeatability? That I also work on Chameleon project with Jason, who gave the talk a couple of talks ago. And we're also going to do for Fabric Jira Hub as one of the primary ways to interface with it. And I suspect in the same theme of us just borrowing everybody else's software wherever possible, that I can see us adopting at least the Chameleon method, but potentially just the Chameleon, their actual services.
Right. It's good both for interoperability as well as for our.
And it's another way. A thing that I say, the way to describe it sometimes is that like Fabric itself, you could do an experiment using only Fabric, but those would probably be the less interesting ones. It's the ones that actually connect to other things that are interesting, right. And you might have a big thing that you want to connect to it and do a cool experiment, but most researchers don't have that, and so that's why it's key for Fabric to connect to things like Chameleon and Cloud Lab and all of these like general purpose facilities that regular researchers can also get an account on there and then get hundreds of compute cores if they want to do some, experiment that looks like the machine room and then connect it to their campus or whatever, right? So having us work seamlessly across all this is really important. Yeah.
Do you foresee people using the FPGAs in a way that also has some sort of reproducibility? Like if I program my own FPGAs, then obviously I'm in complete control of what's running there and I can worry about that myself. But if I was to use the FPGA, there's the way the BU professors are using it, for example, to maybe implement MPC, then I might not be controlling that FPGA myself, but I might really care about using the expedited MPC on that FPGA hardware. How do I keep track of the fact that they've changed what's on the FPGA inside? Or is that my own problem and not Fabric's problem?
I think that for the moment, our programming model really presumes that you own that FPGA. So if you want to load their code, their bit code into your into the device that you acquired by requesting it, then that's fine, and that's part of your experiment, right?
But it's not FPGA as a service.
No, it is basically PCI device as a service. Really, is what we're doing, right? There's we'll just stop there.
Yeah, it could get really hairy.
It does. It's.
But it's really cool as a feature.
There's a red line. There's a red line that I like to talk about, which is what I didn't want to talk about because it's a soapbox of sorts. There's a red line that every designer of a testbed has to make very clear where it is, as to when the testbed ends and experiment begins, right? And there is every advantage in putting that line as low as possible, but not too. It's a Goldilocks kind of thing, right? Not too high, not too low, just right. Because the lower the more you open up of kind of different programmability, but at the same time, lower interfaces are less convenient to program. Steeper learning curve, et cetera, right? But then if you create these very complex programming abstractions, they may be very suitable for a narrow set of experimenters, but then everybody else was like, well, I can't get to the underlying things, and I'm just going to walk away. So
there's a question about authorization and authentication that is up your alley, Ilya.
Right. So this is something we spent a fair amount of time on, this authentication, authorization, and it us being academics, we bring stuff from other projects we worked on, right? So we looked at things like Keystone and a number of other systems, and in all of them, what we ultimately rejected was the fact that they were very centralized. There's a single authority that gives out a role, and we wanted to get away from that. We wanted to actually very explicitly enable multiple sources, multiple trusted sources of attributes on an identity, which are then can be used in a distributed fashion by policy enforcement points that look at those attributes, look at some other metadata, and say, yes, you can do this, no, you cannot do this. And then, because we didn't want to invent our own language or our own software for doing this, we picked up Execmol, and there are a couple of very robust implementations. Surprisingly, I think both of them are out of EU. Somehow it hasn't really picked up interest in the United States. So one that I mentioned in my picture, and that's the one we're using right now. It's called Auth-Z-Force out of a project called Fireware. And then there's another one called Balana. My evaluation of them showed them to be pretty similar in capabilities. So it was, I picked Auth-Z-Force just because I was somewhat more familiar with it at the time. But the good thing is, as with open source projects, always there's a risk, right? What if it just dies out? So having two was actually a very positive thing, because we can say, well, there's some risk mitigation here. If one of them goes away, there's still another. Please do. Yes. Just what is fabric.net? I'll try to make it very easy to remember.
Well, thank you guys. This was fascinating. I really love this topic.
Bye.
Yes, thank you. Thank you for questions. Thank you for inviting us. Bye-bye.